All right, good afternoon, everyone. I'm grading the midterms, but I'm not done yet. About halfway done. So let's get back to our discussion of optimization and gradient descent. We might almost finish this unit today, but if not, it's not a big deal. So just to review where we were talking about the gradient descent algorithm, which is going to be the workhorse type of algorithm that we'll use for optimizing parameters in machine learning. And the idea in words is that you initialize somewhere and then you take small downhill steps until you reach the bottom. To know what is downhill, we remember that the gradient points uphill, so we just need to move in the negative gradient direction. So here's the gradient, here's the negative, and then to make sure that we're taking small steps, we can have this alpha k, which is going to be a small enough positive number here. And then the rest of it just says you take wherever you're at the current iteration, you move downhill a little bit, and then you set that to be the place you move to, and then you just repeat, keep moving downhill, downhill, downhill. All right, any questions on this overall idea? Okay, so there's all sorts of enhancements you can make to this to make it faster and so on. We'll talk about one later today, but this is sort of the main idea behind most optimization techniques. The next thing we did is we convinced ourselves that this does actually work. If the step size is sufficiently small, we were able to prove that the cost at the next step is less than or equal to the cost at the current step. And then we started working on how do we compute the gradient, which we need for gradient descent. How do we do that for this binary cross entropy loss, which is the thing we saw in binary classification. And what we noticed about this overall optimization problem, or the cost function, is that it's a bit complicated, but it becomes more tractable if we think about it in two stages. So first, we have a linear stage that takes us from our weights W to our scores Zi. And then second, we have a nonlinear but separable stage where the cost is written directly in terms of the Zi's, but it's just a sum over all the I terms. So it's a sum of scalar terms. Each one depends on a single Zi. So exploiting the fact that this is linear, that simplifies things, and exploiting the fact that this is separable, that simplifies things. So this is how we wrote the overall cost then. To compute the cost J of parameter vector W, we can think about first computing Z from W, and then once we have that Z, we compute this separable function F, which is just sum over some Fi's of the Zi's. And once we have it split up this way, we can use the multivariable chain rule that says dj dw is df dzi times dzi dwj summed over all the i's. And so one way we can think about this, just maybe graphically, is we have these parameters wj, which are the things we're trying to optimize, and we have the cost, which is what we want, to minimize through optimization. And we can realize that each of these wj's affects all these different zi's, and then the zi's are what directly affects j. So here you can see, like, from a given wj, that affects all the zi's, and all those zi's affect j. And so when we do this chain rule, we need to consider all these n different paths through this diagram, and that's why we have a sum I going from 1 to n. Okay, so that's the multivariable or multivariate chain rule. We'll be seeing this a lot more, but this is the first time we're seeing it. Any questions on that idea? Okay, and then in terms of making progress, we just need to figure out what are these terms now for our cross entropy loss. So we were looking at df dzi. So from here, if I'm looking at the gradient with respect to one particular zi, you can see that only one term in the sum is going to matter. It's going to be the fi term. So we can focus on the fi term, which is this. And we take the gradient of this with respect to zi, and it's not too bad. We get this expression down here. And then we just rewrote it to avoid having two exponentials. We wrote it like this. And then we also need this dzi dwj. So for that, we took this expression and we rewrote it using our A matrix, because the A matrix is a nice way to incorporate that column of ones. So we rewrote it like this, and then now from that expression you can see dzi dwj is just simply aij. Okay, so those are the two pieces of this, and so now in principle we can just put those together and we can compute all of our gradient parameters. Okay, any questions on that? All right, so then the next thing we were doing is we were just looking at the implementation of this. So we're building a Python function here that is taking in the parameter vector x as well as our data x and y, and it is basically computing, first of all, the cost as well as the gradient. So we want to do this as efficiently as possible. So typically that means we're going to break things up into what's called the forward pass and the backward pass. In the forward pass, we compute some important variables like given w and given our data, which determines our a, let's actually compute what are the z's that we're working on. And then once we have those z's, we can compute the cost. And once we have the z's, we can also go back and compute the gradients, which depend on those z's. And so I just want to go through a few of the computational details. We want to do this as efficiently as possible, so we don't want to have any for loops in our implementation here, because for loops are going to be really slow. So we want to write this in terms of matrices and vectors. So, and we also want to avoid repeated computations. So let's first take a look at this. So this is the first thing we're computing, this over here. And let's see. Sorry, I said it wrong. So the first thing we're going to compute is this fi. But looking ahead to what we're going to have to compute later, which is the gradient, we can see that they're kind of similar but kind of different. This has log of 1 plus ezi, and here we have a 1 over 1 plus e minus zi. So let's try to figure out a way where we can compute, where we can essentially re-express this in terms of this term here, so that we only have to compute this once instead of doing this separately and this separately. Okay, so to do that, we start with this expression over here. And let's sort of massage this until we get this in the form of this. So to do that, first of all, notice that if I move this to the denominator, I can compensate by putting a minus in front of the log, right? If I put a minus in front of the log, that basically inverts this. So that moves this to the denominator. Second, we want to put this in the numerator. So if this is in the numerator, when you evaluate this log, this log is going to cancel this e, and putting this in the numerator is like adding minus zi to this expression. So we can compensate for that by adding positive zi. That will cancel the minus zi. Okay, so then those two things are equal. And this is what we want, because now if I multiply top and bottom by e to the minus zi, I get this, which is in the form we will need for the gradient. Okay, and it didn't really make the computation of this much more difficult. So, okay, so that's how we get these fi zi's, and then we just sum them together to get our cost. So let's look at how we do this in the code. Oh, I forgot to mention we also need to compute z. Okay, so in the code, in order to compute z, we want to use a matrix vector multiply. So we first create our A matrix by stacking a column of ones next to our X matrix, which we assume was given. And then that gives us our A matrix, and then we can just do A dot W to compute our Z vector. Next, we want to compute this quantity here inside the log, which is going to be called Py. So it's 1 over 1 plus e to the minus z. And this is a NumPy exponential applied to this whole vector z. And NumPy is smart enough to basically, even though this is a vector, it's going to treat all this as if it was like a scalar divide, scalar add, and so on. So this is going to give us a vector of these quantities over the different i's. And and then the very last step is just to sum those terms. So you can see we're going to have this is NumPy sum 1 minus y times z, and then we have minus log py over here. Okay, so that's going to be summed to get j. So you can see we have a pretty efficient computation of j. Next thing is to work on our gradient. Any questions on how we computed j? Okay, so let's work on the gradient next. So the gradient, we want to do this. But we don't want to have a for loop implementing the sum. We want to do this with matrix multiply. So let's figure out how we can write it as a matrix multiply. So here we have the expression from the previous page. We have derived that this is just aij, so we can plug that in. And from above, or actually, from the previous page, we know that we derived this expression for df dzi, so that is over here. And to avoid writing out this kind of long expression, let's just refer to this whole thing as the ith term in the gradient vector. That's what the gradient vector with respect to gradient of f. So this is like df dz. Okay, so if that's the case, that this is the ith term in the gradient vector here, here's the sum over I, and so these are just the terms in this gradient vector we're computing. So let's say we look at the 0th term, j equals 0. So I put a 0 there, I put a 0 there, and you can see I'm going to have, this is going to be like a vector inner product with another vector. So here we've written it, sum over I, one vector times another vector. So you can see I can write this as the vector of the a's and the vector of the gradients. So that's what happens for the first j. All the other j's here, I just changed the value of j, but they all have the same form. So really the only thing that changes is how we create this A matrix. We're just using different j's for the different rows here. And then this vector is always going to be the same. It's just this stuff. Okay, so at the end of the day, we look at this and we say, oh, okay, that looks like our A matrix, but notice that the first index, which we're calling I, is actually moving across the columns, not the rows as we would expect for the A matrix. And so really this is A transpose. So the second one is j is going down that way. So this is just A transpose times the gradient vector for f. Okay, and that's something we already computed that. Did we compute it? No, we almost computed it. So here's how we compute the gradient vector. It's just py minus y, simple as that. And then this gradient with respect to w is just A transpose dot df dz, which is that. Okay, so you can see we have this very efficient computation of the constant gradient. This is important because when we're doing gradient descent, we're going to have to compute this maybe thousands of times as we take these small little steps, get closer and closer and closer. So we want this to be as efficient as possible. It also could be, the depending on how big your data set is, this A matrix could be really big. So again, we want to just make this as efficient as possible. Okay, so this sort of explains the code, but you'll have a chance to do similar things in the homework and in the lab for this unit. I realize there's sort of a lot going on here, so it might make sense to just look at it on your own time when you get a chance. But are there any questions I can answer now? Okay. So there is one thing about this approach that is not so efficient, which is the fact that here we are recreating this A matrix every single time we do a gradient step. So that's not really efficient. We don't really need or want to do this, to redo this every time. So we would like a method that can do this once at the beginning, store that A matrix, and then only do the rest of the stuff every gradient step. So to do that, we can't use this simple Python function. We need to do something a little bit more sophisticated using a Python class. So I think most of you guys have seen this object-oriented style of programming, but basically this class or this object we're creating is sort of a container that has various things in it. It has functions in it. It also has data stored in it. We have been using these a lot with scikit-learn when we've been doing like linear regression. That object, that's also a class. And the way that it works, or the way that you set it up, is, so here you see class, we're going to call this one logistic fun. And a class must have this initialization code called a constructor that is run by default when you instantiate that class. And then you also put in, of your own design, you put in several other functions, one or more other functions like this. We're building jeval, and jeval just contains the rest of the code from here. And for the initialization or the constructor, that is where we're going to construct the A matrix once when we instantiate this class and then store it internally. All the variables that are stored internally have this self.prefix. So what this initialization code does is it takes in x and y, it stores y internally, it computes n, the number of samples in the data set, but n is really just sort of a temporary variable. It's not stored internally. It doesn't have the self-dot thing. But we do use it to create this A matrix, and we do store that internally as self.a. So that occurs when you do this. So you're calling logistic fun, you're giving it the data, so then what it does is it runs this, it stores A and Y internally inside this lowercase log fun. And then when we want to compute the gradient and cost for a particular vector W naught, we call this method, logfun.jeval, and you can see it calls up self.a and self.y and uses those, computes the cost and gradient, and reports them down there. Okay. So it's just a more sophisticated way of doing things where we can do this once, add initialization, and then never have to redo it again. Okay, so is this stuff you guys have seen before? Hopefully. Okay, any questions on this? All right, you can actually do this in MATLAB too. MATLAB has all the same functionality. It's a really nice way to code things. It's a very clean way. Okay. So a common thing when you're implementing stuff like this, it's relatively complex, right? There's quite a lot. We had to do this whole derivation. It's certainly possible to make mistakes here in terms of the derivation. Then we had to code all this stuff. It's certainly possible to make mistakes in coding. And at the end of the day, maybe we're going to get something that just has bugs in it. So how do we figure out if we have some bugs? There's a nice way of doing that, which leverages the linear approximation that we've been working with. So this is the linear approximation that says if you have a vector W1 that's near W0. The cost at W1 is approximately equal to the cost at W0 plus the inner product between the gradient and the difference from W0. So what we can do is we can just randomly create, let's say, a W0, and then randomly create a W1 that's close to it, and move this to the other side, and then make sure that the left side is approximately equal to the right side. And if that checks out for random W0 and W1 close to each other, there's a very good chance that we coded things correctly. Okay. So how close these quantities are going to be when you evaluate them depends on how close W1 and W0 are. So we'll see an example here. So first thing we do is we figure out how many features do we have. Then we create a W0 vector of that number of features plus 1 because of the intercept term. So now we have just a random W0. It's a good idea to use random Gaussian, random normal for this. Then we make W1 close to W0 by making another random perturbation, but multiplying it by a very small number like 1e minus 6. So now these guys are close to each other. And we separately evaluate our cost and gradient at W0 and W1. And then we can compute this thing, which is the gradient at W0, inner product with the difference. So we'll call that DJ predict. And we want to make sure DJ predict is very close to the left side, J1 minus J0. So we just print out those values, and you can see that they agree to at least 5 decimal points here. How many they agree to, like I said, depends on how small the step size is. You can see there's a very good agreement. If you printed out more decimal points, eventually they would not be exactly the same because this is an approximation. But this convinces us that, yeah, things are coded correctly, we can move on. If you do this and this fails, you don't want to move on because when you run gradient descent, you are not going to be converging to the minimum of your cost function. You're going to be doing something crazy. It's not going to be working. So if this doesn't work, you go back and you look at your code, you look at your derivation, you do whatever debugging you need to do to try to figure this out. So you'll need to do this for lab 6. You'll actually have to do the derivation as well as code it for the lab. So it's definitely the most challenging lab of the semester. Please do start it early, lab 6. Not do this week, do next week, next Friday. Friday in 10 days or whatever. Okay, so this is a nice trick to just sort of debug your code, make sure everything is working well. Okay, any questions on this? Okay, great. So, so now we're finally ready to program gradient descent itself, and that's really easy because the algorithm is so simple. So essentially we just have a for loop where we iterate over the number of gradient steps, and we just alternate between, okay, so first of all we initialize where we're going to start. And so in this case we're just assuming that this function is given the initialization. So we're initializing our W vector, here we call it W0 at W init. And then we alternate between computing the cost and the gradient at W0 and doing our gradient step. And here we're just overwriting W with W0 with the new W0. So we're just overwriting it over and over again. And just as a way to visualize what's going on, we are going to store what happens along the way. This is totally optional. You don't necessarily need to do this, but often it's a good idea. So here we are creating what's called a Python dictionary, where we are appending the value of the cost, mainly so that we can plot it to see what happened as we were optimizing, as well as the values of our parameter vector, so we can look at those if we like to. So the way that, there's many ways to do this. The way that it's being done here to create this dictionary, this is not going to give you NumPy quantities. So what we do is after we've finished all our iterations, we're going to go through and convert both of these quantities to NumPy arrays, and then we can easily print them or plot them or whatever we want to do. Okay, so essentially that's this really simple program. It just iterates that gradient descent loop, and we can see what happens. Any questions on this one? Okay, so let's take a look at a plot. So we have to choose some hyperparameters. So let's choose a step size or a learning rate of 1e minus 4 as just a guess. And we'll also choose to run this for 2,000 iterations. And you can see basically this is just one line of code. We tell it the learning rate, the number of iterations. We give it the function that computes our constant gradient. We give it the initialization. In this case, the initialization is just going to be random. And here we're running it. We're plotting the loss, J, versus iterations. And you can see that the loss is decreasing, which is great. But you can also see that it is not finished. It is still making progress at 2,000 iterations. So that's not great. Ideally, this thing would have sort of bottomed out. So we have a couple options. We can either run it for more iterations, but maybe we're impatient. We can also see if maybe the step size is too small. Maybe we can increase the step size, take bigger steps, and then in 2,000 iterations, maybe we can reach close to the bottom of the function. So that's what we'll do. Other thing I want to point out is we are plotting this on log. So log x, log y, that's generally what you want to do in this case, because if you plot it in a linear manner, the plots look very boring. They kind of look like this. You can't really tell what's going on because there's not much change here, and there's a big change at the beginning and then not much. So by plotting it log, you can really kind of zoom in to what happens and see that, yes, this is decreasing. But it's not finished. It needs more work. Over here, we also are computing the test accuracy. Once we're done optimizing, we have our W vector. Then we can do, so this is given a new test vector. We're doing x.w, adding the intercept, and then that gives us our score. To convert our score into a binary prediction, we just do this logical thresholding at 0, and that will give us a logical y-hat, return that. So so this is what we see, and the next step is to look at different learning rates. Any questions on this page? Okay, so let's look at what happens with different learning rates. So the orange one here is the same as the last page. So that is 1e minus 4 that we saw before. So you can see that if we slow the learning rate, or if we use an even smaller learning rate, 1e minus 5, we have this blue curve, which is nice and smooth, but it's even slower, right? It's even at a worse spot after 2,000 iterations. So let's go the other way. What if we increase the learning rate by a factor of 10? Then we have this green curve. The green curve is interesting. In one sense, it does seem to be a really good option because it converges here within 2,000 iterations to a lower value of the loss. In fact, it sort of looks like the loss is bottoming out, so maybe it is finding the minimum. That's great. What happens along the way, though, is maybe not ideal because you can see actually for the first 2 iterations, the loss actually went up, right? It overshot and actually got worse 2 iterations in a row, and then somehow it did make progress, and then it overshot, made some progress, overshot, and so on. Eventually it did sort of settle down, but on the way there it was definitely not minimizing the function at every iteration. If you go even further and you double that learning rate, then you get this red curve. And the red curve you can see is behaving in a much more crazy way. it is spiking up to very high levels of loss and then coming down again and spiking up and so on. And it's never really settling at the bottom. It's getting close to the bottom and it keeps overshooting it, overshooting it, overshooting it, never actually getting into the very bottom. So that's why that red curve looks like that. Okay. So you can see here there's a range of learning rates and the basic trend, if it's too small, slow convergence. If it's too large, instability, overshooting. So the question then is, what is the best learning rate? It's sort of a tricky thing. In practice, it's not an easy problem. When the cost function is convex, we'll talk about convexity later today, which actually it is in this case, we can do something more sophisticated, which I'll describe next. We can actually adapt the step size at every iteration in a way that guarantees that we will make progress. So we'll talk about that next, but in a lot of machine learning problems, it is not a convex cost, and there is no real great way to choose a step size, so you have to basically just try different values of step size. We'll talk more about that later when we get to neural networks, but generally speaking, it's not an easy problem. But for convex, there definitely are things we can do. So that's what we'll talk about next. Before we move on, are any questions about step size? Okay, so very important. You can see it makes a huge difference to get the step size right. Okay, so we're going to now look at an adaptive step size approach. There's various ways to do this, but we're going to cover what's called the Armijo approach or Armijo rule. It's a little bit non-intuitive, so let me describe it here with some math and then some pictures. So it all starts with this equation that we derived when we were analyzing gradient descent, and we were trying to figure out whether gradient descent is actually going to work. And this is the equation, when we looked at it, we convinced ourselves that yes, if alpha k is small enough, then this term will overwhelm this term, and the middle term is negative, so that's what we want. We want the cost to go down, and so we want that this last term is smaller than the middle term in order to make progress. And we said we can do that by choosing alpha k small enough, because when alpha k is small, squaring it makes it even a lot smaller. Okay, so this is sort of where we're starting. So what the Armijo rule does is it sort of focuses on the first two terms of this, but it actually inserts another parameter called C right in there. So keep that in mind. Now we're actually going to insert a parameter C in there. C is something we have to choose. For the moment, let's just assume that it's 1/2. So what Armijo does is it says, for some current guess of your step size, alpha k, you try to take a step. You essentially compute using gradient descent, your new W. At that point, you can measure the cost at the W you have of your new step, and you can check to see whether this inequality holds. Okay, check if this inequality holds. If it does hold, then great. You accept that step and you proceed onward. If this fails, it's a sign that your step size was too large. And you actually say, okay, let's redo that step. Let's throw it out. Let's decrease our step size and try again. And try with the smaller step size to see if we can make this work. So now let me show you the picture that explains what is going on here. So here's the picture of our cost function as a function of the step size. So, and this is for, so this is the cost you'll get after you take a gradient descent step with step size alpha k. Okay, so remember if alpha k is really small, we're in this regime here, this is the equation from the previous page. Maybe I'll highlight it. Okay, so we know that when alpha k is really small, this alpha k squared term can be ignored because it's so tiny, just forget about it. So at that point, this function, if you think about it as a function of alpha k, is linear. So for very small alpha k's, you will see this red curve. That's what this is. For very small alpha k's, you just see proportional to this is how much the cost is decreasing. Okay, so if alpha k is 0, obviously nothing is there, you just start here. So this is the cost, J WK, your old cost. Now, as alpha k starts to move away from 0, that red curve comes down, but in a very linear way at the beginning. As alpha k gets bigger and bigger, this starts to take effect. And eventually, you start to get a quadratic type shape in alpha k because of that quadratic. As alpha k starts to get bigger, as we know, eventually you overshoot. So at this point, when alpha k is greater than whatever value this is, your cost after adaptation is actually higher than when you started. So that's overshooting. If alpha k is to the right of there, that's overshooting. So we definitely don't want to do that. We want to make progress. We want to choose alpha k small enough that we're somewhere, ideally in this range here, right? That's what we want to do. So the whole idea behind the Armijo rule is that, okay, we know that this dashed line is the first two terms. So if we put in this c in front of the second term, where c is a number between 0 and 1, whatever slope that is, this blue line has c times that slope. So if this is slope 1, the blue line is slope 1 half, or slope c. So here is so that's the Armijo line. This is the thing we're checking. So you compute, you have a guess of alpha k. You take a step, a gradient descent step. Now you know what your new WK plus 1 is. You measure the cost. And you check, is it below that blue line? Here's the blue line. If yes, you're good. If not, you were too aggressive. So the alpha k's that are going to be under the blue line are the ones where this red curve is under this blue line. So for all these alpha k's, our Armijo rule would say, you're good to go. That was a valid step size. Do that and move on. On the other hand, if you were to the right of here, our Armijo would say, nope, this guy is above this, so this inequality fails, and throw that out. Try again with the smaller alpha k. So maybe, if this is your alpha k here, you say, oh, try again with the smaller one. So then maybe you have it, and now you try again, and yes, for that alpha k, you will pass. Okay, so that's essentially where this criteria is coming from. It's this blue line here. Okay, so let's come back to the previous page. So again, this is the Armijo rule. At each k, you choose some step size alpha k. I'll add compute WK plus 1, and check if this is satisfied. If yes, you know that your cost has decreased, right? Because you're somewhere in this range. So your new cost is definitely better than when you started. I guess there's a technicality. If for some reason you are already at the optimal solution and your gradient was exactly 0, then this whole term will be 0, and your cost will just stay at the optimal solution. So no problem there. Okay. So yeah, so this is the whole idea. This Armijo rule decreases your cost by a fraction c of that predicted by the linear approximation. So what is predicted by the linear approximation is this dotted line. This is like c, factor of c of that, and so you're guaranteed to be somewhere in there. So then here's the logic. If the rule passes, you accept that WK, and in fact, now you might wonder, well, wait a minute, maybe I have been too conservative. Maybe I've been stuck at an alpha k that's too small. So, maybe you're somehow over here. And you don't want to be over there because you're making very little progress. So what you do is the next time you say, let's try a slightly bigger step size. So over here, if it passes, you accept this. And the next time you actually increase your step size a little bit. Usually you do this by taking the old one and multiplying by some number that's slightly greater than 1, like 1.1 or something like that. So now your step size is going to be slightly bigger. And that way, if you somehow started with some step size of too small, over the iterations, you will eventually get into a good range of step size. On the other hand, if the rule fails, then don't accept that new WK plus 1, just essentially overwrite it with your old WK, and in fact, decrease your step size compared to what it was before. And you can do that by multiplying the old one by some number less than 1. Typically a number like 0.5. Once you're too aggressive, you just want to make a big correction and just get back into a regime that is working again. And then you can slowly grow it. Okay, so that's the approach. Yeah, that's Armijo. Okay, are there any questions on the methodology? Let me show you a picture of what's happening. Maybe it will make a little bit more sense. So this is the code. We won't go through it. It just implements that procedure. This is maybe more interesting. So here we have the loss over the iterations. And you can see the loss is always either staying the same or getting better. Down here, we have the learning rate, or the step size. We started at 10e minus 2, and that was too large. So what happened is the first 2 steps of Armijo failed. And so we actually said, okay, have the learning rate. That failed, so we have it again. Finally, now it's 1/4 of where we started, we passed, and the cost decreased, the loss decreased. And actually, the loss decreased for a whole bunch of steps, for about 30 steps. And so over those 30 steps, the loss was decreasing. And so we were gradually seeing if we could handle maybe a bigger learning rate. So we're gradually growing the learning rate. Eventually, it got too big, and it failed again. So we decreased it by a factor of 2. And then it successfully made 1 step, but then it failed again, so we decreased it again. And then it made a whole bunch of successful steps, after which we gradually increased the learning rate, and so on. So you can see that we're failing a couple times, then successful for a bunch of times, failing a couple times, successful for a bunch of times, and so on. If you look kind of globally what's happening, it's interesting that the sort of step size that we want at the beginning is, not very big, maybe somewhere between 10e minus 3, 10e minus 2. But as the iterations go and we get closer to the minima, we actually can tolerate larger step sizes, like this is 10e minus 3. We can actually tolerate like 2 10e minus 3. So that's one of the nice things about adaptive learning rate, is that the step sizes that are optimal are not always the same. Like sometimes in one part of the cost surface, it's steeper and you don't want to have as large a step size, but then somewhere else it's more shallow and you can afford to have a larger step size over here. So Armijo learns that and figures everything out. If you look at the loss after 2,000 iterations, it is better than any of the fixed step size methods we had tried, so that's nice. And the test accuracy is a little bit better too. Yes?
Can you explain why in the beginning it like grew pretty slowly, but at the end it seems like it grows fast and then
Well, remember
Is it
that,
just the log?
so we have a log plot, so,
Yeah.
you know, like, this is 10 iterations, this is, 100, this is 1,000. So, there's like 90 iterations here, there's 900 iterations here, so that's why these are getting sharper and sharper.
Okay.
I don't know if is that
Yeah.
the answer? Okay, yeah. Okay. So, all right, any other questions? Yes.
So will the loss always be better?
So yeah, so sometimes it stays the same because we reject the like hypothesized step we were going to take, tentative step. We say, nope, the loss would have increased, so we're not going to take that step. We just basically have like a failed step. So we move forward, we move from this to this, but the cost, we just keep it the same because we keep the W vector the same.
I guess what I meant was, is it always better with the adaptive step versus the fixed step, or is it just kind of based on these?
No, yeah, it's this. There's nothing optimal about this. It's just a practical technique. It's pretty popular, but it doesn't have any optimality that I know of. Yeah, it's probably usually going to be better, at least for a convex loss. Yes.
I know it doesn't really matter for this class, but in other iterations of this algorithm I've seen, the step size changes differently.
Yeah.
Basically like alpha k resets every time, and then there's a separate loop that brings it down to be appropriate. Is this one harder to prove convergence on?
Yeah, I actually don't know whether I don't know whether this has a convergence proof, but yeah, there's many versions of this and many other approaches to adaptive step size. So it's just one that works pretty well in practice, but yeah, there's other things we could try as well. Okay, so maybe another thing we could talk about is what is the effect of this C parameter, because this is something we have to choose. So when C is 1/2, this line is half the slope of this. So that means you can see that it gives you this, in this figure at least, it gives you this admissible range. Let's say that we chose C as 1/4. If C is 1/4, then we have this line, which now the admissible range would be bigger, which is good, right? Less of a chance we'd fail. However, for some of those, the cost we get is maybe not quite as good, because here, yeah, you can see that these costs are not as good as those costs. So basically, this C parameter is not so easy to choose. It's something that I think setting it at 0.5 is a solid approach. You can play with it. It's going to depend on the exact problem, what's the best value. But you can see, just graphically the effect. If C is too large, let's say C is very close to 1, then you have this line here, and then your admissibility region is quite small, and also there's not much reduction in the loss here. So, definitely there's an issue if C is too large. That's not going to work well. If C is close to 0, then you have this whole region here, which means the only time you consider step failed is if you really overshot. That could work okay, but then sometimes you're going to, half the time, you'll be still overshooting, not bad enough to make the cost increase, but bad enough that you're over there. So there's various tweaking you can do to the C parameter, but you can kind of get a sense for the values here. And then these are tuning parameters here as well. I typically set this at 0.5 and this one at 1.1. Okay, so that's the Armijo method. Any other questions? Okay, so one question that sometimes is asked is, well, why don't we do something else? Why don't we come back here? Why don't we just choose like a grid of several alpha k's? and just try them all. So maybe if those are my alpha k's, then I would take steps of all those different sizes. I would get those different losses, right? And then I would just look through and choose the best one. So at that point, I say, oh, this is the best alpha k. That is a step I'm going to take. With that step, you can see I have the best loss, so everything's good. Well, the trouble with that is you've had to do a lot of work to test all those alpha k's. So if I make a grid of 10 values, I actually have to do the same amount of work computationally as 10 separate updates. I could have taken 10 steps in the amount of effort that I was really tweaking this one step. I wanted to make this one step perfectly, but I could have actually made 10 imperfect steps. I probably would have gotten a lot faster. So the nice thing about the Armijo rule is that if it's set up right, the fraction of failed steps is pretty small. You're not wasting a lot of failed steps, but but still you are kind of learning a good step size. So like if you look at how many failed steps we have here, in the first, here's 1, 2 failed steps, 3, 4. So within the first, what is that? 50 or 60 iterations, we only had 4 failed steps. So, it's less than 10%. So I don't know what the average is, but, let's say on the order of 10% of the time we're failing, but 90% of the time we're actually making good progress. Also, we're learning a pretty good, maybe not optimal, but pretty good step size at every iteration. So that's what's nice about this method. It's very practical. So that's, so this is this thing I was just describing. Okay, so that's really all I wanted to say about the Armijo rule. Any last questions about it? Yes?
It doesn't have a full form because it seems very similar to the time series model. I mean,
The time series model for what?
the autoregressive moving average, it seems very similar. So
Autoregressive moving average is, I don't know, that to me that's just sort of a time series model that it's not really an adaptive step size thing. So sometimes, let's see, in the lab 6 actually uses a model that is very similar to autoregressive in its formulation, although I don't think it's called that. And there's not a time series, but there's sort of like, it's a model that has exactly the sort of ratio of polynomials form. Sometimes, I don't remember if I did it this semester, sometimes in unit 1 or 2, I put an ARMA problem on the homework. I can't remember if I did that this semester or not, but it's not something we'll be focusing on, but it's just, it certainly is a model that you can use. It's like a ratio of polynomials, so we've talked a lot about polynomial models, but it's just a ratio of polynomials model. So it's good for some applications, bad for others. So yeah, it's just one of the many things we could use as a model. Okay, great. So maybe the very last thing I'll talk about briefly is convexity. So several times in the course, I mentioned that we'll eventually talk about convexity. So let me just very briefly talk about it now. So before we talk about convex functions, we need to talk about convex sets. So a convex set is a set for which any 2 points in the set that you choose, if you consider the line segment between them, then any of the points on that line segment are guaranteed to be in that set. So here's a non-convex set. So some of the points create line segments that are inside, but I can find some points here where the line segment between them actually goes outside the set. Okay, so this is a non-convex set. This is a convex set. No matter what points I choose here, all the line segments are inside the set. Mathematically, we can call the set D, and this is how we create that line segment. We have T as a number between 0 and 1, and this is just this is called a convex combination of those points. It is, Yeah, it's just a way of making a line segment between x and y. Okay, so that's convex sets. Examples of convex sets: circles, squares, ellipses. The real Rn space is convex. A hyperplane in Rn, a half space in Rn. Those are all convex sets. These are ones we often see in this course. Now that we have convex sets, we can talk about convex functions. So a function is convex. So this is a function, first of all, that's just outputting one real number. There might be many inputs, but a single output. Okay, so first of all, we need that the domain is a convex set. Second, we need that this holds for any t, x, and y. So this says that if you average 2 points at the input of the function, that needs to be less than or equal to if you average the points at the output of the function. So let me try to illustrate this. So here are 2 points, x and y. And this is, let's say, some average on the input of the function. So x and y are inputs to the function. This tx plus 1 minus ty is an average of those, a t-weighted average. So if I plug that into the function, I get this point here. This is the vertical axis of the function, right? So on the other hand, I could look at x going through the function, in which case I get this, fx. I can then look at y going through the function on its own, in which case I get fy. And I could also do the averaging in the output space. So I could do this t-weighted average of those 2 points, in which case I would get this blue one. Okay, so convexity says that this output average point here is always going to be greater than the input average point, or greater or equal to the input average point there. So that's convexity. So it's often drawn like this, with the function like this, and then you can see that any 2 points on that function, you can create a chord like this, and it's never going. The function is not doing something like that. If it was doing something like that, then we found some points here that violate this rule. So here's another picture: convex, non-convex. Okay, so that is what convex functions are, the mathematical definition. Some examples: anytime you have a scalar linear function, sometimes people call this affine linear, these are convex. If x has several inputs, it's a vector. That's the version of that affine linear function. If f is quadratic, that is convex as long as the a coefficient is non-negative, the coefficient on the x squared. And this can be generalized to non-quadratic functions if you say that if the second derivative exists and is non-negative, that's very much like this in spirit. The second derivative of this function would cancel out these, and you would just get 2a. So this idea for generic functions, second differentiable functions, is sort of like an extension of that. If you have multi-input functions, then you can extend that by looking at the Hessian matrix. The Hessian matrix is a matrix of all the second derivatives. So that matrix now needs to be positive in the sense of a matrix, or non-negative, which is positive semi-definite. Okay, other things that we have seen in this course: norms. So whether it's the L1 norm or L2 norm, the norms are always convex. If you have 2 convex functions, you can add them. Their sum is convex. You can even compose convex functions, although, so f and g need to be convex, but then the outer one, f, also needs to be non-decreasing. And then that guy is convex. And finally, various things we have seen. So RSS is convex, binary cross-entropy loss, and their versions with L1 or L2 regularization, those are all convex. Okay. The reason we care about this is just if f is convex and it's a local minimizer, and X is a local minimizer, and then X is also a global minimizer. So we don't have to worry about bad local minima. We can just optimize our function, look for the point, the minimum point, and we know that that's going to be the global optimum. There's extensions of this that work also for non-differentiable functions, but we won't get into those details in this course. So there's one other topic, but I'm going to save that for Wednesday. We'll finish it quickly, and then we'll move on to the next unit. So see you guys on Wednesday.